in chemistry.
I'm in biochemistry.
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 Great, welcome. Are you excited?
Yes, I'm so excited.
Hello everybody, I'm Tiana Rai. I'm a director for the School of Molecular Sciences, and I'm delighted to welcome you to this new fall semester and this kickoff of celebration of science. And I think after the year when we did a lot of adapting by learning remotely online, meeting remotely online, we were ready to meet in person, but safely mask to mask rather than face to face. So I'm really excited to share with you this celebration of science where you're going to see how we enjoy fun of science and how we enjoy to trick the atoms to show us, the molecules to show us their unique properties. So without further ado, I want to introduce you to Ian Gould.
Okay, good morning everybody, welcome. We're really delighted to see you. I know you were dying to come back to campus, we were dying to have you back in campus. And you know, this semester, you're going to learn about chemistry. And learning chemistry actually is kind of like hard work, but it's rewarding work. You like to put hard work in and you get something back. So learning chemistry is hard work. So we're going to do some chemistry today, except today, we're not really going to do the hard work, right? We're going to make it fun so we can actually enjoy it today. Like no hard work today. Plenty of hard work coming ahead. So we're going to show you some chemistry. We're going to have you making some observations, but mainly it's kind of for fun, right? Like I say, my name's Ian Gould. I have several of my friends and colleagues here. We have Ara, I'll stand up. Ara teaches in our organic chemistry program. And Rebecca, stand up. Ashley, stand up. Ashley also teaches in the general chemistry program. And then we have our maestro of DAOs, Glenn. Sparking lab coat, just like me. And we also have a couple of our advisors here because, you know, the school isn't the building, right? The school isn't me for sure, or Ashley, or Clem, and Ara, but it's, you know, it's all of it, right? It includes all the other people who help you learn, not just instructors, the advisors, and more importantly, includes you, right? So you're now part of us. Chemistry's for everybody, right? So the advisors like doing chemistry too, don't you guys?
We do.
All right.
Morning. Hi, my name is Jessica. I'm the assistant director for the advising services. We're located in Armstrong Hall on the humanities and social sciences side. So if you have questions, come see us. So as we talked about, we know that in chemistry, matter is important. And we also know that matter can't disappear. So we're going to take this, we're going to dump it. I know you guys are teeming with excitement, right? Right? Does it matter what happens right now, huh? So we're going to see what happens. We're looking, we're checking. How many of you guys think that fire is going to come out? Take a guess. Fire? We're good? No fire? All right. All right, so let's see what happens. Oh!
Okay, and I am Sarah, another one of the academic advisors that you'll be working with. So we also know that chemistry is all about chemical reactions, right? But with chemical reactions, you can tell it happens because you can see it. But you do have to look very closely. So everyone who's here with me with glasses, you have to look closely. And what did you see happen? All right. Sometimes you do have to add a little something else to see that reaction. There we go.
Chemical reactions, things happen at the atomic and molecular level, right? Who can see atoms and molecules? Well, you can't, right? You know that we're surrounded by them. You can't see individual atoms and molecules, can you? So when the atoms and molecules change, how do you know? This is actually, you have to take part in this. I'm not going to go into somebody. How do you know if something happens to the atoms and molecules? You can't see them. For example, you might see, what did we just see? Yeah, color change. Yeah, something like that. So there's various other kinds of things that you can do. So even though we can't see the atoms and molecules, we can tell things happen at the atomic and molecular scale. And historically, that's what chemists did, right? They made observations and figured out all kinds of amazing things. So let's do a little bit more experimentation, and we'll be looking very carefully if we can see any change, okay? Nothing, right? Nothing happened, right? No close enough. Let's try again. It's just chemical reactions, right? There's no magic there. We understand exactly what's going on. The reactions are a very fundamental kind of reaction. Those are reactions between acids and bases. Because after all, everybody knows acids react with bases, right?
Yes.
Do we all know that? Yes. Right, everybody. Do acids react with bases? Everybody?
Yes.
They do. Why? Why do acids react with bases? You kind of think that might be important. What do you think?
Neutralize each other.
Yeah, but why do they neutralize it? What happens at the atomic level? Guess what you're going to learn this semester? So this is the point, right? So you know things like acids react with bases. Don't you think you need to understand at the absolute atomic and molecular level exactly why that most fundamental of things happens? I think you do. I think you do too. That's what you're going to learn this semester. Welcome to ASU.
This looks exciting. So I have a tradition when doing demos. I start out by saying, "Hey, class," and then all of you enthusiastically and loudly reply, "Hey, Jim." All right, got it? Let's give it a shot. Hey, class!
Hey, Jim!
Today, we are going to look at the gas laws. So these are the laws where we look at the pressure, temperature, volume, and number of moles of a gas. Now, the first gas law was developed back in 1662 by Sir Robert Boyle. And he looked at the relationship between the pressure and the volume of the gas. So to illustrate that, I have this simple piston, which kind of looks like a syringe between two blocks of wood. Now, let's think about this. When I decrease the volume, what's happening to the pressure inside that syringe?
Increases.
Increases, correct. And that is the inverse relationship between pressure and volume. Well, so what? What can we do with that? Well, I happen to have right here a Boyle's Law apparatus. So, again, when we decrease the volume, pressure increases, but then we put that gas into your bike tire so that you can make it to class on time. It's always a good thing. Also, you are experiencing Boyle's Law right now. Every time you breathe, think about what's happening. Your diaphragm drops down when you inhale. Your ribs rotate upward and outward. That increases the volume of your thoracic cavity, decreasing the pressure inside. That allows the higher atmospheric pressure to push in, expanding your lungs. Then when you exhale, the opposite happens. Your ribs rotate downward and inward, your diaphragm pushes upward. That decreases the volume, increasing the pressure, and you exhale. So think about that, Boyle's Law and breathing. You're experiencing it right now. Also, last summer, I got my scuba diving certification. And one thing that they warned us about is when you're down at depth and you start to ascend, if you hold your breath, Boyle's Law goes into effect. And as you ascend holding your breath, the pressure is decreasing, the volume in your lungs is increasing, and you'll rupture your lungs. So, not recommended to do. So Boyle's Law definitely has some important considerations. So we go from the 1600s to the early 1700s, when Guillaume Amanton looked at the next relationship between the temperature and pressure of a gas. About 100 years later, Joseph-Louis Gay-Lussac looked at the same relationship, but with better instrumentation. Sometimes you'll hear it referred to as the Gay-Lussac law, sometimes Amanton's law. Either way, it's still the relationship between the temperature and pressure of a gas. So to illustrate that, this device measures pressure. It is sealed, so no gas is going in or out. It's rigid, so the volume stays the same. So right now, atmospheric pressure is just under 15 pounds per square inch. But when I put it into the liquid nitrogen, which is about negative 300 degrees Fahrenheit, what is happening to the pressure? Decreasing, exactly. You may have experienced this with your car tires, where overnight it got cold, you get into your car in the morning, start it up, and the pressure warning light comes on because your tires got cold. Then as the day heats up, and this is an illustration of Phoenix in the summer. Now, or you start to drive, the gas molecules then heat back up, and what happens to the pressure? Increases. Yep. And it's going up, right? I can't see it from now. Okay. Good. There we go. All right, so that is the direct relationship between the temperature and pressure of a gas. As temperature goes up, pressure goes up, and vice versa. Okay, now we'll move to about 1787, 1789. French scientist Jacques Charel. Here in the United States, we pronounce it Charles. So you may have heard of Charles' law. And he looked at the relationship between the temperature and the volume of a gas. So I've got a balloon, or hydrogen balloon, put it into the liquid nitrogen. So let's think about what's happening. Is any gas leaving or entering the balloon? No. Is the pressure changing? No. This is an open container under 1 atmosphere of pressure. That's not changing. What happens to the volume, though? Okay, decreasing as it gets colder, The gas molecules move more slowly, impact with less force, and the volume decreases. Now, do hydrogen balloons float? Unless they're cold. Then, as the gas heats back up, the volume expands, the density decreases, and then it floats again. The volume's increased back to where it was. Well, so what? Well, this is what drives weather. Okay, the storms we've been having. Sun heats the air, rises, expands, cools, and then that allows the humidity to increase, and then boom, it rains. Okay, so that's what drives weather on Earth, whether you're looking at the global Hadley cells or local thunderstorms. Also, ocean currents are influenced by changes in density, and also just the convection within the Earth itself, the tectonics. So the earthquake recently in Haiti, also due to density differences within the Earth. So some very important processes here. Now, the last gas law will go to the early 1800s. This is Amonton's law. And that looks at the relationship between the number of moles, or the number of gas molecules, in a vessel, a container, and its volume. You may have done this one, actually. So I need a special elastic container, which I happen to have right here. So I'm going to put moles of gas in this right before your very eyes. Was this worth waking up for?
Yes.
Right here? All right, highlight of your day, I bet. So, Avogadro's law says the more moles of gas you put in, what happens to the volume? Increases, right? Seems pretty obvious, doesn't it? And I'm sure Avogadro's friends were like, well, duh, Lorenzo Romano, Medio Carlo Avogadro. That's obvious. But what's not so obvious is that when you have equal volumes, you have an equal number of moles of gas, irrespective of the gas. So what's in that balloon? Hydrogen. What's in this balloon? Yeah, exactly, right? So nitrogen, some leftover oxygen, carbon dioxide, probably some water vapor. But for me this morning, mostly vodka. So, what Avogadro's law tells us that when you have equal volumes, you have equal number of moles of gas. So 1 mole of gas at standard temperature and pressure will occupy a volume of about 22.4 liters. You'll hear that again this semester. All right, now something that's just really cool, not really one of the gas laws, and this looks ahead to what I'll be doing later with intermolecular forces. Okay, I'm going to put that balloon in here. Now, this balloon had hydrogen. Hydrogen is very small molecule, H2. So the intermolecular forces in here are pretty weak. And this stayed as a gas. Now, in the balloon that I blew up, there are larger molecules. Some of them have hydrogen bonds, they're more attractive, giving us, voila, liquefied Jim's morning breath. One of the rarest substances on Earth. Anybody like to try some? No? All right. Just pour it out. Waste it again. So there you have the gas laws. And up next is Ara to show us how to flash.
Good morning. So as I get set up, who brushed their teeth this morning? Not Jim. Well, I better, yeah, clearly. Vodka. Let's see, show of hands again. Better be everybody. Okay, if it's not said we need to sit far apart from each other. How many, well, show me, how much toothpaste did you use to brush your teeth? Not this much. You don't want to be, to be wasteful, right? Toothpaste when you're a college student can cost a lot because it's going to be 4 years of you saving money and budgeting yourself, right? So let me see how much toothpaste you think it's going to take to brush an elephant's teeth. How much? That much. Okay. Okay, let's see. Let's see. Oh, let's guess. Let's participate. Oh, that much. Oh, that's a good one. This one. Okay. All right. Well, let's make some toothpaste, okay, for our elephant friend. And then we're going to ship it all the way. Oh. Do you think we need more?
Yes.
Because that's about, how much it's going to take for one elephant, right? So more. So let's make more. Oh! Ooh, that was a really bad one, isn't it? We'll have to gather all that up and ship it over there. Should I do it one more time?
Yes.
Yes, definitely. Oh, there it goes, there it goes. Yay, okay. So who's gonna gather all of that and ship it to Asia where the elephants live, where Thailand? Who's ridden an elephant before? Oh, Debbie has. Oh, Sarah has. Okay, so hopefully one day you'll get to ride an elephant because it's quite fun. And you don't realize how large they are unless, they're right beside you and how tiny you are. Okay? But this is a very simple decomposition reaction. We basically had hydrogen peroxide. Now, in order for this reaction to go faster, what did I add?
Potassium iodide.
Yes, but what is that acting as in this reaction?
Catalyst.
Catalyst, very good. So we all know that, right? Even in high school, or maybe you've taken an AP chemistry course, we all learned about catalysts. And so we're going to take a more in-depth look of how catalyst works in a particular chemical reaction. And catalysts are very important, you guys. So you're going to learn that all throughout your years here at ASU in your chemistry course. Okay?
My name is Rebecca, and I'm excited to be here today with you. So I won't make a mess like that. That'll be fun. I'll get to introduce to you a chemical, an element that a lot of people are familiar with, and that is hydrogen. Many of you might know its chemical symbol. Do you know the chemical symbol for hydrogen?
H.
Yes. Good job. You're ready for chemistry. Even the atomic number, right? Do you know the atomic number?
1.
Awesome. Okay, so yeah, it's the first element in the periodic table. It's the lightest element, and it's also the most abundant element in the universe. So that's exciting. It's easy to recognize. You're familiar with it. It's odorless, colorless, non-toxic, highly combustible. That's fun. When it burns, it produces water. So that's really good. And its name derives from the Greek hydro, that means water, and genus, that means forming. So hydrogen means forming water. And hydrogen has been produced since the mid-1600s. And scientists used to pour acid onto metals, and then they were able to produce hydrogen as a gas. But it wasn't until 100 years later when a British chemist was able to identify that it was an element. His name was Henry Cavendish. The combustion of hydrogen is more exciting. And you probably have heard that hydrogen is used as a rocket fuel. Yeah, so it's interesting to think about that, just having hydrogen reacting with oxygen that produces water can power a space shuttle. Isn't that like crazy? And we only produce water. So now I have here some balloons. And in this balloon, it's the one that Jim used, I think. What do we have in here?
Hydrogen.
Hydrogen. What do we have around us in the classroom?
Oxygen.
Plenty of oxygen. Where's the water? Where's the reaction? So you will learn in chemistry that hydrogen is not very reactive. It's a very stable molecule, right? So that's why nothing's happening. But we still think of hydrogen as being very dangerous, and we should, because it powers space shuttles and stuff. So I'm going to add something, a little something. So I'm going to add a little bit of energy to it, and let's see what happens. Do you guys want to see?
Yeah.
Okay, for this one I'm going to wear my goggles. I'm going to keep them apart. I'm going to come closer. And I'm going to make this a little bit bigger, longer. Should we make another one?
Yes.
It looks like I have enough over here. Another one. Just gonna help me here. Get over here. Okay, so remember, just hydrogen and oxygen with a little bit of energy. Pretty cool. Let's do a bigger one. Hopefully we won't set the fire on. We've done that before. So hopefully this does not happen. So this is a little bit bigger one. And try to see. Okay. Careful, Jen. Let's see if you can see the water that's forming. Ready? Should we count? 3,
2, 1.
Whoa.
Sure, why not?
Okay.
It's a waste of water.
I know, right?
Otherwise, we have to take it to the lab, and we don't want to do that.
I just blow it up in the lab.
No, we don't want to do that, Jim. Get in trouble. Okay, this is the last one, so here we go. Oh, that was loud. Okay. Thank you, guys. So now, that was good.
I think that looks good.
Okay, so Ashley's gonna help me.
Okay, so what we have on here right now is something known as lycopodium powder. And if you were to touch it, it's made from like spores, so it's a very, very small, very slippery. You probably have felt this like maybe if you put on a pair of gloves or other things made out of latex. Yeah? Okay. So what we see from this is that something like this, what we see from this is that if we were to actually try to light it, and we got a little bit of something there, but for the most part, it remains just kind of a pile of powder there, right? But what happens is that if we begin to aerosolize this, spread it out in the air, it has a property that makes it pretty combustible. All right, so as a pile there, it doesn't do much, but let's see if I can do this. This is my first time doing it, so I need some moral support. Can you guys cheer me on? Am I good? Yeah? All right, here we go. Let's see. Oh, maybe I need another one, but you can kind of see it's getting there. I got scared. I didn't hear enough. I didn't get enough pumping up. All right, let's try this again. A little bit closer. All right, here we go. Let's see. Gotta really get it this time. Woo! Right on my eyebrows. Oh, that's why I wore goggles. So what's really cool is that whenever we begin to put things into a flame, I don't know why they let me have fire, by the way. I'm just walking around with this like, I talk too much with my hands. All right, so I'm gonna set that there. Okay. But what's really cool, in addition to getting things hot in here, we're also gonna get you guys a little bit excited. Now, not in that way, but we're gonna excite some electrons, because when it really comes down to it, electrons are a big focus in our chemistry classes, because a lot of chemical bonding has to do with electrons. So, in addition to that, all the atoms have electrons, and they're arranged in orbitals around a nucleus. So, whenever we begin to see and we understand what those electron organizations look like, a lot of times electrons exist in a very relaxed state. But I promise you guys excitement, right?
Yes.
We are to excite some electrons. And so a lot of times a good way to do that is with fire. Also, you know, give things energy, also electricity and stuff, but fire's more fun. So I have a bunch of metal salts here, and you guys are gonna actually probably recognize this from some celebrations that involve fireworks, right? So we're gonna use this fire to excite the electrons for the metals in these solutions. So let's see here, what do I wanna start with? Let's start off with something like sodium chloride, right? You guys know what sodium chloride is. You know what sodium chloride is?
Yeah.
Salt, right? Everybody got salt, but this time it's in methanol to make it a little bit more of a punch for you guys. So you guys ready?
Yeah.
All right, here we go. Uh-oh, I got turned on. Okay, psych. All right, here we go.
Ooh.
Yeah, what color are you guys seeing?
Orange.
Orange, really bright, vibrant orange, right? Very cool. So then, let's see here. Do I got
What's the direction we spray this thing?
Huh?
It's going in this direction.
Sorry.
Spray that. Spray towards her.
You guys don't want to be. I thought that's why they're all sitting in the back. You guys knew, right? All right, so that was sodium chloride. We have this nice kind of distinctive bright orange color. Didn't light anyone on fire, my apologies. All right, we have strontium chloride. So we are looking at strontium and what happens when we excite those electrons. Does anyone know what color strontium burns? Do you want to find out?
Yeah.
Okay, now I'm scared.
Whoa.
So, hey, welcome to ASU.
Yeah.
Right? But I have 2 more bottles. You guys want to see them?
Yeah.
Okay, let's see. Here I have potassium. All right. Eat your bananas, right? Keep you from getting muscle cramps. Yeah. All right. So potassium. What color do you guys see there? Violet. Yeah, it's like a nice lavender, violet, purple. This is one of my favorites. I saved the last 2 that were my favorites for last. So this one definitely a top for me. And then copper. You guys know what's coming. This is great. This is my all-time favorite right here. Does anyone know what color this should turn? Kind of like a green or a blue is kind of like the typical characteristic of copper. So let's see.
Whoa.
It's like Halloween already, right?
Yeah.
I guess we could like say early Christmas. Right? I don't know. They don't let me out much. All right, so hopefully that was exciting for you guys. If not, at least your electrons are excited.
So the liquid nitrogen here is about negative 300 degrees Fahrenheit. And molecular nitrogen N2. Right, so what is the atomic, or the molecular mass, or what's the atomic mass of nitrogen? 14, good, there's no periodic table. 14, so N2, 28. Right, so this is boiling very rapidly right now because there isn't very much force holding those molecules together. So they warm up and they just spread apart, go from a liquid to a gas. Now right next to that, you just saw me pour out this water that was boiling. Okay, H2O. What is the atomic mass of hydrogen? Rebecca told you this.
1.
1. So you've got 2 of those. How about oxygen?
16.
16, good. So 2 plus 16?
18.
You are ready for chemistry. Okay, so this had a molecular mass of 28, this is 18. So if we were just looking at the London forces, the attraction based on their mass essentially, this would have weaker London forces, right? But how hot do you have to get water to get it to boil? Okay, 100 Celsius to 12 Fahrenheit compared to, okay, this is negative 300 Fahrenheit. So why is it so much harder to boil water compared to the liquid nitrogen? okay, hydrogen bonds. And that shows you just how strong those hydrogen bonds are. The temperature has to be 500 degrees Fahrenheit higher to get water to boil compared to liquid nitrogen. So that illustrates that very well. Now, where'd our droppers go? How often do you have two substances near each other that are about 500 degrees apart? Not too often. So, would you like to see me combine those?
Yes.
Two liquids? Yeah. And what do you think will happen?
You have to do without droppers, Tom.
No, we're gonna do it without the droppers. Fine.
You have created one.
All right, you ready? Okay, here you go. 1, 2. Well, they're getting me a dropper. After all that work, I guess I should use the dropper. Thank you. You're so efficient. Okay. Ready? Here we go. Ooh. Okay, that sucked, right? So let's try this then. Whoa! Not terribly impressive, is it? Well, you ever hear the expression, go big or go home?
Yeah.
All right. This one I'm definitely going to put some goggles on. So I need a little bit more liquid nitrogen, a little bit more hot water. I'm pretty good at getting into hot water. Let's see if I can use it. So here we go. Here's some liquid nitrogen. And then here I've got hot water. Does anyone know a redneck's last words? Hey y'all, watch this! So here we go. Give me a countdown from 5, please.
5, 4, 3, 2, 1.
That's it. That's what I have to show you today. There was actually a real science behind every single one of those. And every single one of those you're actually going to learn about either this year or next. And, you know, the whole point of this is, like I say, that when, like acids and bases, why do you care? We know acids react with bases, but why? How do you predict what's going to be an acid? How do you predict what's going to be a strong acid? How do you use that information to do something useful? How do you make something new? Right? That's what chemists think about, what we do every day. We're going to enjoy working with you. I'm so delighted to have everybody back on campus. I hope you enjoy working with us. So we're done. Can you just thank everybody today, and then we'll see you all in class at the end of this week.